What's up, you scholars of the Enlightenment? Welcome back to the channel again. I'm a little bit rushed today. The government is chasing me down because I have to do my self-assessment tax return.
Taxes! Taxes! Beautiful, lovely taxes!
The life of a renegade freelancing scientist, I'm afraid. But that's for me to worry about, not you. Today, I did want to get something out. So what I want to share with you is something a little different today. So one of the things that I do is I run my own science show. And it's a science show with a little bit of a difference, because instead of teaching people the facts about a particular area of science, it's designed to get them doing the scientific method, to get them thinking scientifically for themselves. So it's a show where we go through all the steps as it purports to finding the Higgs boson. I take it into schools, I take it into adult venues, and the idea is that the crowd make a hypothesis, they collect data, they go through cognitive biases, they analyze data, and then they get results. So it's kind of a stealth learning project. They go through the scientific method all the way from start to finish and do it themselves instead of just learning rote facts. And I think this is a really important thing for our kids to learn, to think more scientifically and think more critically. So it's a show that was born out of a similar show that I did at CERN and the Large Hadron Collider in France and Switzerland. And then off the back of that, the Science and Technologies Facilities Council, the Ogden Trust, and a few others in the UK gave me the funding to write this show and take it forward. And that's what I do part of the time. So I got a recording of the show, and the recording is what I'm going to show to you. So I hope you enjoy it. I'm going to cut out some, it is quite a long video, so I'm going to cut out some selected highlights a little bit later today when I find some time after this tax return. But I hope you enjoy it. Any feedbacks, gratefully received. And here we go.
So, who's ready to do some science?
Me! Woo!
Good, but we can do better than that. Who's ready to do some science?
Woo!
Excellent. Excellent. That's the sort of attitude I want today, right? Because we're going to be testing some of the things you've learned and also rediscovering a Nobel Prize winning particle, the Higgs, right? It was the 10th anniversary of the discovery of the Higgs boson last week. You're going to be rediscovering it today for yourselves, right? That's going to be the role of today. So my name is Dr. Sam Gregson. I'm a high-energy particle physicist from the University of Cambridge and the Large Hadron Collider. Now, usually, I would ask, who's heard of the Large Hadron Collider? But I think pretty much everyone, right? Given what you've been doing. And today, you're going to be rediscovering a particle for yourselves using your particle physics knowledge. Exactly. And, right? There's no problem with shouting out and carrying on today, right? I want more of this, right? And using my laptop at the front. So, start nice and simple. Everything around us is made up of atoms, yeah? Protons and neutrons in a central nucleus with electrons whizzing around the outside. But that raised another question for us particle physicists, right? What are those particles made of? Are they made of something smaller underneath? Now, usually, if you have something macroscopic, a watch, a clock, a pair of glasses, and you want to know what's inside, how it comes together to make up the whole, what would you usually do? Right, before I break it, I'd usually put a screwdriver inside, right? And see how the pieces come together to make up the whole. Now, with atoms, we don't have a screwdriver small enough, so what do? Exactly right? So, we smash the thing apart, right? And we see the little pieces that come together to make up the whole, right? Now, this is what I want you to remember about particle physics, right? If you remember nothing else, this is what particle physics is. Smashing stuff apart, seeing the little pieces that come out and how they go back together to make up structure in the universe, yes? If you remember nothing else about what particle physics is, that's what you need to remember. Now, when we wanted to find the tiniest building blocks of atoms, we built this beautiful machine, the Large Hadron Collider, a 27-kilometer long tunnel under France and Switzerland, which smashes protons together at nearly the speed of light, right? So we've got one coming one way, one coming the other way, and they smash together in the Large Hadron Collider. Now, your first job today is going to be to power this thing up, right? Simply power it up, get it working, so we can go looking for new particles. So, I've got a couple of little games for you to play. So if you can get your app back up, and I should be able to just go to that, come back up, right? Your first game today is going to be to power up that Large Hadron Collider. Now, first question. I don't know, right? Who knows how we get protons whizzing around the LHC at nearly the speed of light? Should have been one of the things you were taught in your masterclass sessions. How do we get these protons whizzing around at nearly the speed of light? What do we use?
Explosion. Accelerator.
We do. And what do we use within that accelerator?
The magnets.
Now everyone falls in this trap. The magnets are used to guide things around in circles, as you saw in one of the lectures, make things go in circles. How do we make them go fast?
Explosion.
Explosion's a good idea, not quite correct. Yeah, electrodes, huge, powerful electrodes, very, very high voltages, right? Now, your first job, I'm going to open it for players, is going to be to power up the Large Hadron Collider's voltage systems, high voltage systems. So, start. What do you think you need to do? You all have some controls, right? I want that high voltage powered up as quickly as possible. Now, this is very, very easy, but what's the problem going to be?
It's too hot.
Stopping, right? Now, this is what I want to get you used to. Science is all about working together. All of you have a button. All of you have control. But you have to work together. Now, what would be a good way to solve this problem? Talk to one another. What would be a good way? Right, right. Everyone stop. Who's going to do it?
No.
Who's going to do it?
Everyone stop. Everyone stop. Man, this is
Right. Stop trolling. Stop trolling. Stop trolling. Come on. I want to teach you that science. It has to stay. It has to stay. Stop. Right. Whoever's doing that, I want you to stop.
Stop being cheeky. Stop.
We got stop. Stop. Good. Right. That is the first activity done. Right. Now, question. You've already told me. How do we make things go around circles? Magnets, right? So very strong magnetic fields can make these charged particles turn around circles. And this is what we want to do at the Large Hadron Collider. Get them going in circles so that they can go round and round and round and smash together more frequently. Now, how do we make those magnets incredibly powerful so we can get things that are traveling at basically the speed of light going around in a circle? What did we learn? I saw that you learned it because I was stood in the back. That's right. But how do we make the magnet super powerful? Superconductors. They are superconducting magnets. How do we make these materials superconducting? Right, exactly right. We make them super cold, right? At the LHC, we use a coolant called liquid helium. Now, why do we use liquid helium? Because it never, ever becomes a solid, right? Doesn't matter how cold you make it, it always stays a liquid. Some of you might have heard of 0-point energy, right? The 0-point energy of helium is enough to make it a liquid. So we can use it as a coolant all the way down to basically absolute zero. So your next task is going to be, again, working together to power up those liquid helium systems. So what do we think we have to do this time?
Okay, so it has to be an order.
Right, so stop. Everyone stop, please. Right, it will call you out. If it's your turn, it will call you out, right? I'm going to turn off the sounds a second, right? I'm going to explain what's going on. Right, are we listening? Stop, please, because that sound is so annoying when it keeps going off all the time, right? So you each have a number. Good, well done. It's really funny, I know, right? Good. But I need to tell you what's going on. Right, I can turn off the sounds. Oh, no, I can't. I need to do it over there, right? So we need the numbers in order. This is a game I like to call delayed gratification, right? So what I need is it powered up in order. And the idea behind this game is in science, you all have a role, but you all have to come together to get to the goal. Everyone has their own role, their own skills. So I want to see us get to 27, please. And please don't troll. Please stop trolling. I don't know who's doing it, but it's not funny. Come on, let's try and get up to 27.
If everyone takes like 5 seconds before they go.
Right, just relax, yeah? You're young, you got plenty of time ahead of you. Nice and calm, yeah? Somebody's joined, that's why, but don't worry about it. Number 1, now 2. Good. 3, good. 4, good. 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 7, good. 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 I know somebody's going to pop out at 26. I know. 3, 24. Good. Good. Hey! Yes, of course, somebody wants to play afterwards, right? So, stop now, because that will keep going, and I don't want it to keep going, right? So, stop, come on. Right, so Alt-Tab. Right, I should actually be able to turn off the sound, I think, right, if I really need to. So, really good, right? So that's the first set of games. Really well done, right? So really well done. So we got the LHC powered up. We got those high voltages powered up, right? So here they are in a particle accelerator, very high voltage electrodes, which fire those charged particles along and speed them up so we can smash them together very strongly. We also have magnets, right? These magnets bend the particles around corners into a circle so that we can keep passing them past each other and get them to collide. To do that, we need very strong magnetic fields. We need to cool these things down with liquid helium and make them superconducting, right? That's very important. Now, science is very collaborative. There's also a competitive edge sometimes, right? So, yes.
I know that other scientists do other scientists.
They do. Our friend is apparently still going, right? So, we got one more. Stop that, please. Right. Good. So, it's all right. It's all right. I can chill them out a little bit. Right. I can. Whoops. sound off, right? So they can cool off a little bit. Right, here's what I'm going to do. So I've got one competitive game for you to play. So I'm going to stop this. I'm going to close this. I'm going to come back in. Right, we are going to play a different game, right? Now, you're going to play a little bit competitively. You're going to get those particles flowing along in the Large Hadron Collider. Now remember, we've powered up those electrical systems, we've powered up those magnets. What you now need to do is make your proton, you can find your number, it's on your phone, this is a test run. Get your proton down that beam pipe safely so that it can interact at the end. So, this is a test run, we will start again. On your phone, you should have the number in the middle of your controls. We'll tell you which number you are. Alex has already gone, right? Rio is gone. Right? Nami's gone. Right? So, this is a nice little test. Do we understand?
Yeah.
Right. So, you are basically controlling the magnets of the particle collider, and you have to get your proton safely down the tracks. Understood? Good. That's what I like to hear. Right. So, now we're going to play for real. Are we ready? Right. Good. Now, let's see if we can get...
We have to get time to put up.
Let's see if we can get some music going.
Music.
Right. I'm going to need some Tron. Why is it not coming up on the screen? We will get to that. We will get to that one. Don't worry. So I'm trying to get this Daft Punk to play if I can. The doesn't seem to want to come up on the screen. All right. So we're going to do it without music, I guess. Right. So the music doesn't want to play, which means you have to be noisy. Can you do that for me?
Yeah.
Right, good. Are we ready?
Yeah.
So you get 3 lives apiece. When those 3 lives are lost, you're out. Are we ready?
Yeah.
Remember, the number that you are is in the middle of your screen on your phone. Give me a countdown from 3.
3, 2, 1.
Off we go. So, let's get as many down the pipe as we can, please. Good. Nice. Kai's in the lead at the moment. Kai's still got 3. Richard's still got 3. LH Corin, which I like, still got 3. Nice and quick. Good. Right. 100 seconds left, so 2 minutes. It will get faster, higher energy, bigger turns. Oh, Liketha's gone, unfortunately. Good. Keep it nice and close. Good. What we do with the LHC is we actually have bunches of protons that are stuck very close together. This helps us to make sure that they collide. So this isn't too unsimilar to what you might see in a beam pipe at the Large Hadron Collider. Obviously, the magnets would change the position of each proton, not individually, but as a group. But this is essentially what you get. The beam pipe wouldn't be as curved and changed as this, but it's essentially the same thing. Richard's gone. Good. TK's up front at the moment. Kara just behind. Ruby, Josie. Good. Last 50 seconds. Dewey Day's gone. Come on. It pushes you back into the middle. When you lose a life, it pushes you back in the middle, which is not really realistic, but we want you to keep playing. Alex is gone. It's getting harder now. Harder and harder. Last 30 seconds. Nice. Hold it together. Josie's out in front. Where's Josie? Where's Josie? She's concentrating. She's concentrating too much. Good. Ria's out in front now. Now, listen. Final instruction. Whoever's closest to the front, if you're still alive, when it hits 0, is the winner. So make sure you're up front when the timer hits 0. 4, 3, 2, 1. Where's Ria? Have you been conned? Oh. Ria is our winner. Give Ria a big round of applause. Well done, Ria. One more game or?
Yes.
Are we sure? Right, okay, maybe 1 minute, because we need to get into the science, right? So, we'll play for a 1 minute game. Happy with that?
Yeah.
Right, so 1 minute game. Are we all ready? Are we all ready?
Yeah.
Countdown from 5.
4, 3, 2, 1. Yeah.
Let's go. So again, identify your particle. That's the hardest part of the game at the start. All protons are identical. In this case, they're not, just to allow you to identify them. But all protons are identical, and that's why it's so hard at the start to work out which one you are, right? They're all little circles here. So, last 30 seconds. Kara always goes out into the front. Where's Kara? Good, right. Concentrate, Kara. Good. Ikitha's gone again. Well done. Good. Last 20 seconds. Remember, you have to be up front right at the end. Last 15 seconds. It's getting harder and harder, right? Gets faster, more deviations and thinner. Last 9 seconds. 1. LH Corin is up at the front. Hit the wall. LH Corin still winning.
1.
LH Corin wins. Where's LH Corin? Where's LH Corin? Very, very, very fitting. Give him a big round of applause, please. Good. Really, really good. That was awesome. Really, really good.
Bro, they're running through me. Bro, was it, bro? Yeah, I won. Yeah, I definitely.
Excellent. Right. So now we've got the LHC powered on, and we can go looking for new particles like this guy, this little Higgs boson. How many of you have heard of the Higgs boson? Most of you, right? You've heard of it in your lectures, right? We're going to find this, rediscover it today by playing games just like that. You're going to collect the data, analyze it, go through the hypothesis. You're going to go through all the steps of the scientific method to find the Higgs boson. So, you should know from your lessons that everything in the universe is made up of particles, right? These are the Lego building blocks of the universe. And we now know from many years of particle physics experiments that essentially the smallest particles that we know of are not atoms, they're not protons and neutrons, they're actually quarks and electrons, right? So quarks and electrons are the things that make up solid stuff, as far as we're aware. There could be even smaller stuff, but as far as we're aware, the tiniest building blocks of the universe are actually quarks and electrons. We know that light is a wave and a particle. So solid things are particles. Even light is a particle. And what you probably have learned this week is that even the forces between particles are themselves particles, right? So if we put two magnets close together, how do they know to attract or repel? They don't have a brain. They don't know what they're doing. But it's because there's that set of particles going backwards and forwards all the time between them, carrying information, carrying a force. In this case, the photon for the electromagnetic interaction, right? So everything is particles. Solid things, light, and even forces are particles. And using that model and looking at that model, we now know that the universe was incredibly kind. We say it was incredibly economical. It only uses a very small set of Lego building blocks, as Ben, I'm sure, has shown you, to make up the entire universe. The universe could have been much meaner, right? It could have made millions of different types of building blocks, but it only uses a handful, right? It's very, very economical. And they're all of each type, each one identical to the other. So the universe is very friendly in terms of the building blocks that it uses. We have the quarks, which make up protons and neutrons, for example. We have the leptons, like the electron, and we have the bosons, those force carriers that carry forces between particles. And using that model of particles, we can explain everything from very tiny atoms up to the most awe-inspiring galaxies. But there was one thing that we couldn't explain, and you've probably seen this if you've heard of the Higgs boson. We couldn't explain why some of those building blocks had no mass and therefore no weight in a gravitational field, and yet some of them do. We have mass, we have weight. Why is it that some of those building blocks have no mass and no weight, and yet others do? To understand that, we need to bring in this little guy, this little Higgs boson. And you're going to rediscover it today. Because realize without it, our entire understanding of the universe around us, the so-called standard model, falls apart. We assume that this particle was there for about 60 years until we actually found it about 10 years ago, right? So you're going to rediscover that Higgs for yourself. Now, the second set of games we're going to play is going to be collecting data to find that Higgs boson. Now, collecting data with the LHC, I think, is a lot like using social media. Who uses social media? Come on. Come on. Right. Most of you, right? Why is it like using social media? Well, because when we smash particles together, just like social media, we produce, can I get this to play? Is it on the, oh, it might be on the screen. How do I get it to play? Is it push right? Oh, onto here. This one? It doesn't want to play. Does it not want to play on? Oh, on here. I see what you're saying. Yeah. So, sorry about that. Okay, this doesn't want to play. Fine. You've already seen it in your lectures. I guess it doesn't want to play on Windows. I made this on Mac and it doesn't want to play on Windows. So when we smash particles together, right, instead of getting little bits of glass and plastic, when I smash the clock, what do we get when we smash protons together? Who's seen it in their lectures? What types of things do we get when we smash protons together? Don't be shy. There's no wrong answers. We can get all of these things. We can get electrons. We can get protons. We can get all sorts of things. Right, jets. We can get all sorts of things. The point is, when we smash particles together, it's not like smashing a clock together, right? When we smash a clock, we get little predictable things, bits of glass, bits of plastic, springs, things that we expect. When we smash particles together, they disappear in a ball of energy, and then that energy creates loads of weird stuff, right? It's a bit like if I smashed a clock and got, you know, a tennis ball, a carrot, and Boris Johnson at the back or something, right? So I get all of this bizarre stuff, right? And I want to filter it down and only keep collisions that produce new things that I want to look for. For example, a Higgs boson, right? So what you're going to do is you're going to play, there are some old slides in here, right? They need updating, right? What you're going to do is you're going to look at some real collisions from the Large Hadron Collider, and you're going to filter them down and only keep the ones that probably contain these Higgs bosons that we want to study, right? Now, Higgs bosons tend to hide in collisions that produce leptons. Electrons and its heavier cousin, the muon. So you're all familiar with electrons, right? Now, I'm going to split you up into two teams. We're going to go a little bit collaborative in your team, but a little bit competitive between teams. Make sense?
Yeah.
So everyone on the right of the middle, and you can kind of decide which way you want to go, right? Is going to be on Team Atlas. Are we going to decide? Give me a cheer, Team Atlas. Come on, she's doing 90% of the work. Give me a cheer, Team Atlas. Better, right? And everyone on the left of the line is going to be on Team CMS. Give me a cheer, Team CMS. That was good. That was good straight out of the gate, to be fair, right? That was very good, right? So, what are these two teams? Well, these two teams were the two experiments that were looking for new particles, like the Higgs boson, at the Large Hadron Collider. Here's a picture of Atlas, right? It's over 70,000 tons of steel and electronics. There's a little chap at the bottom here for scale, over 15 meters tall. So huge, huge machines. The protons come in, one out of the television, one into the television. They smash together, They produce all of these weird particles, and the particles hit the sides, and we can see what's in those collisions, what was produced in those collisions. They're a little bit like digital cameras, right? We smash protons together, and we take photos of all the particles that come out to see if we can find anything new. Question?
What does Atlas have? Was it just like a name of this book? Right?
I forget this, but it's, I will look it up and tell you at the end. Atlas, what does it stand for? I forget.
A toroidal LHC.
Yeah, like apparatus system or something.
Yes, yeah.
Yeah, I forget, yeah.
Toroidal LHC.
Yes, so it's to do with the shape. So it's a toroidal LHC apparatus system or something. I forget the name. I will tell you the exact answer, but it's to do with the shape. But they always pick these really cool names, right, of Greek gods and things like this, titans, to name the experiments. So here's an example of one of those digital pictures you get when you have a particle collision. The particles come in, they smash together, they disappear in a ball of energy, they produce all of this yellow, rotten rubbish that we don't want to see, because we've seen it before. But occasionally, it produces these beautiful green and red lepton tracks. And that tells us that maybe a little Higgs boson is hiding in this collision. So, next game, next interactive activity. I'm going to need some volunteers.
Me? Oh, volunteers.
Good, that's what I like to hear. Right, from both teams. In fact, we have just about enough to do the whole team, right? So first of all, I want Team Atlas to come down to the front and make a nice line along the front. Be careful, because there's quite a bit of plastic on the floor, which I didn't realize. I should have smashed that out of the clock to start with. So just be careful with the plastic on the floor. So come down to the front and line up along the wall. So, is somebody going out of the room? It's not that difficult, I swear. Right. So, can we see the screen? Yeah. Can we see the screen? You guys need to see it first, right? You can also play this game in the audience if you want to, but you won't need to because you're all at the front, actually. So let's forget that. So what you're going to be looking for is particle collisions that produce anything with an electron in it. Make sense?
Yeah.
Here's what you're going to see when we start. I'm going to click. They're going to start popping out, right? 1 per second. Basically, whenever you see any green, you're going to come to the front. You're going to click the lower left. So you look at the screen up here. You click the lower left, you go to the back, you go round. That's it. Nice and easy. Make sense? Good. Right, well, I'm going to tell them what they're looking for now. Right? You're going to stand closer in a minute, don't worry. Right, you're looking for anything with 2 reds in it. Right? 2 reds can be loads of other rubbish, but 2 reds. Does that make sense?
2 reds and a green.
Could be 2 reds and a green. As long as it has 2 reds, it can have any other rubbish it wants. Makes sense? Say again. The button that you press is just the normal left-hand button of the mouse on the front of the pad. Make sense? I'm going to leave it in the middle of the screen. Try not to touch the pad at all. Just touch the lower left button. Make sense?
Yeah.
Right. Now, there's one more rule. You must always be wearing these rather swanky LHC hats, right? I bought these all the way from CERN, so I'm damn sure going to get some use out of them, right? So you must be wearing the hat. Make sense? You come forward, so come forward a little bit, stand against the wall. You touch the hat, you go round, you go to the back. You're going to have about a minute to collect as many as you can. Make sense? If you are not fast enough, right, and fast enough is defined by me on a very subjective basis, yes, there will be punishments involved. Yes? Do we understand? Right, we're being smart here. We've got more hats, right? So, are we ready? Remember what you will see is on the screen. So you come to the front. Are we listening? You come to the front, you look at the screen, you press the left button when you see what you want to see. 2 reds. Make sense? Yes. 3, 2, 1, go. Nice and quick, otherwise there will be consequences. Go! Move! 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 Right, go! Good! but nothing there. Go, pass, wrong. 2, nice, go. Next. Nice, next. 2 reds. There's got to be 2. That's not 2 reds. Move. 2 reds. Good. Well done. Next. Nice and careful with the electronics. Well done. Oh, somebody pressed the right one. Good. Go. Good. That was one missed though. You missed the first one. No, that's wrong. Move. Good. 2 reds. Well done. Go. Nice and quick. No, wrong. Go on. 2 reds. Well done. Go. Nice and fast. 2 reds. Good. Let's go. 2 reds. Nice and fast. Probably about 10 seconds left. Well done. Go. Well done. That is not pressed, I'm afraid. Go. No, wrong. Nice. 2 reds. Well done. Stop. Did everyone get a go? Well done. Right, go sit down. Give them a big round of applause. Well done. Right. Don't worry, for any mess, I will clean up any mess, right? So, get yourself sat down, and I will explain what's happened. You okay? Sorry, that was quite an aggressive spray. But I saw you had glasses on. I was like, you're protected. You know, we can go a little bit harder there. So yeah, I should have put mine on as well, right? So, guys, let's talk about this, right? So what happened? They clicked 20 times, right? They got 14 correct, and they got 6 wrong. Right? That's pretty good. The problem is they missed 21 when they were swapping over, right? And this is the problem. Producing these new particles is probabilistic. And this is why we smash as many particles together as we can. At the LHC, we actually smash 40 million protons together every single second, right? And 40 million times a second, the computer is playing this game. Yes, no, that looks new. Yes, keep. No, no, yes, no. But 40 million times a second. You're doing it 1 time a second. 32.5 is actually really good. The one at the LHC is probably more like 1%, right? So that was really, really good, right? So you killed the LHC basically, right? Now, Team CMS, are we going to beat that? Yeah. Down we come then. So,
Clean chance of the gun and putting it.
The hat is supposed to be too big, right? That is set up in this manner. Right. Left click, right? So you'll have to look at the screen, and you just don't even touch the pad. You just touch the left mouse button, right? Make sense?
Yeah.
So nice and in a row. All you're going to be looking for is any red, right? Anytime you see a red, you will click. However, are we listening? Are we listening? You have seen what you need to do. They went first. What does that mean? That means I will hold you to a much higher standard. Yes? Which means I will be much, much more trigger happy. Yes? Do we understand? Right, you start that off. I will start it off for you. Any red. Make sense? Go. Any red. Good. Off you go. That's a good start. Well done. Nice and quick. Careful, careful. Oh, just, oh, the wrong one! No, don't! Any red, well done, excellent. Nice hustle, good, nice and quick. Oh, I think that was a miss! Any red? Well done, well done. Any red? Well done, go, well done, you escaped. Wait, wait. You didn't press it. Oh, go! Nice and red, please. Red. No hat on. Good, well done, go. Nice and quick. Oh, you pushed off the screen. I'm going to come for you later. Right, red. I'm going to come for you now. Come on, lower left. Well done. Go. Make sure lower left. That was a bit slow though. Lower left. Lower left. Well done and go. Well done. Well done. Well done and go. Well done. That's nice and quick. No, a bit too slow, I'm afraid. Nice. Well done. Stop. Good. Give them a big round of applause. You can go and sit down. Well done. Well done. Are you okay? Good. Right. Well done. Right. Good job. Right. Really, really, really good. Right. So, let's have a look. Very similar, right? They clicked 20 times again because there's the same number of events in each set. They got 14 right, 6 wrong, which is very similar, and missed 23, right? Very, very similar scores, but really, really, really good. At the end, I will show you who did the best in this game, right? But I will tell you now that it's very, very close. I can see in the results. So, all of that data, all of your clicks, is basically saved in my computer, right? And we'll see who won in a little bit of time. Now, before we do that, so here was the example I was going to show you, but you saw it on the screen, right? Before we reveal who won, we need to walk through those steps of the scientific method to discover that Higgs boson. So we collected some data, but that's not enough. We need to learn how to analyze it. And I need to introduce you to what I like to call the beauty of the scientific method. Yes? This is Albert, yes, Uncle Albert, with a little bit of my Photoshop, right? Albert Einstein, right? It's not a real picture in case people are concerned, right? So, why is the scientific method such a beautiful thing? Well, because using that little clicking at the front, which seems like a very silly game, that clicking is actually based on real Large Hadron Collider data, right? So using that clicking, we can actually prove today that there is a new particle in this room, right? If you do well enough on the challenges, right? And you've done really well so far. So I need to introduce you to the scientific method. What's the first step of the scientific method? Anyone? Good, very, very good, right? Very good. So, it's all right. 2 people can be right at the same time, it's all good, right? So hypothesis making. So we have problems and we want to think of sensible solutions, sensible mind, as to how we might solve those problems, right? And those solutions are called hypotheses, right? Potential solutions to problems. And I like to think of the scientific method as kind of like a criminal trial. Now, in a criminal trial, a defendant is innocent until what? Proven guilty, right? And in science, a hypothesis, we assume it's not correct until we can prove it with enough reason and enough evidence, right? So, I told you that I have a hypothesis, and some of the people in the masterclasses have told you they have a hypothesis, that there's a new particle that you probably hadn't heard of before you came here, some of you might have done, but called the Higgs boson, which exists in this room with us right now, right? That's a hypothesis. It was a guess for a long, long time. Now, first question. Who thinks it's not that important to know what things have mass and what things don't? Good. Excellent. Right? There has to be one. I'm going to show you why it's so important. Paper. A little bit of mass or a lot of mass? Okay, fine. Okay. Plastic balls. A little bit of mass or a lot of mass? A little bit? Yeah. Okay, fine. We're still good. Okay. What about this? A little bit of mass or a lot of mass? You want to chance it?
A little bit.
A little bit? A lot of mass, right? So it's very, very important to know when something has mass and when something doesn't, right? Or I can get myself in trouble, right? I can get myself in trouble very, very quickly, right? So knowing when things have mass and when things don't, where's my pointer gone? It's very, very important, right? I usually do this with frozen peas, but they all defrosted in the bag and it's disgusting, right? So we had the balls instead. Now, I showed you how important it is to know when something has mass. It's even more important in particle physics, right? Because remember this little Lego building block set of the universe that I showed you, right? It looks very, very simple, nice and colorful, not many pieces, right? You could give that to your little brother, your little sister for Christmas, and they can start making the universe from scratch, right? Here's the instruction manual for those particles, right? The standard model, the maths that tells us how those particles go together, right? It's a little bit stylized, but this is the main idea. Here's page 2, right? Not that bad. You're okay with all that, right? It's just maths, right? It's just maths. It's fine. It's all good. Right. Now, I don't want to scare you with that, and I don't want you to worry about that equation. Shh, 1 second. We're going to play some more games shortly, don't worry, right? But I want you to realize a couple of very important things, right? First of all, sections of this equation contain the entirety of human knowledge of various different areas of nature. So if I say to you, nuclear, what do you say? Radioactivity. Say again? Nuclear fusion, nuclear explosion, nuclear bombs, nuclear medicine, nuclear power. All of our understanding of nuclear stuff fits in 5 lines of maths. That's it. That's all we understand about nuclear stuff. 5 lines of maths, right? This part tells us everything we know about structure, because it explains why protons and neutrons bind together and we aren't just a soup on the floor, right? So huge pieces of this equation contain huge ideas and humanity's understanding of the nature around it, right? And notice how many times in that equation this magical letter M appears. What do we think M stands for? Mass, exactly, right? So it's very important. What do we say? Magic? Do we have a magic? Milton, something like this, right? I heard something, right? So M stands for mass. Very important to know where mass comes from. Because imagine if any of these M's was 0, huge pieces of this equation would disappear and we wouldn't understand the universe around us fully, right? So understanding where mass comes from is very, very important. And we didn't know until 3 brilliant theoretical physicists, Peter Higgs, Francois Englert, and Robert Brout, I'm sorry, they are all boring old men, yes, came up with a hypothesis. They suggested that there's an invisible field known as the Higgs field, which exists everywhere in the universe at the same time. Sort of like the air in the room, it's everywhere, in here, in the next room, outside. Who's seen Star Wars? You know about it, right? What is there in Star Wars that we can't see, we can't touch, we can't taste? Padawan. I'm not getting into that area, right? Touching and no, right? We're not doing that, right? But what is there? The Force, right? We're not just not getting there, right? The Force, right? Basically, what these physicists suggested is that there's a force field that exists everywhere in the universe, and the reason particles get their mass, their hypothesis, was that when particles go through this field, they feel kind of like a drag. It's like going through treacle, and that slows them down and gives them their mass. So I need 3 or 4 volunteers Yes, definitely you. Right? To come down and help me show how different types of particles get their different amounts of mass. So, Ben, do you want to choose? Because this is too difficult for me. Go on. You can't choose.
Mr. Taylor, you can choose from the behavior.
Mr. Taylor, yeah. Mr. Taylor, help me out. Come on.
2,
Good.
3.
We'll take 4. Come on, we'll do one more as well. Don't worry, there'll be more games and we can play the other games again. Give them a big round of applause. Come on. Good. Right. Thank you. Don't worry. At the end of this presentation, you get to throw stuff at me, right? So all of this, you get your own back. Don't worry, right? It's coming. Don't worry. So, yeah, you can spray me for 5 minutes or something, right? It'll be good, right? So our friends here are going to show us how different particles get their different amounts of mass. Now, the first question I want to ask you is for the audience. Which one of these 4 is the most energetic? This isn't even hard, is it? Right, come forward a little bit. Come forward a little bit. I will go across. When I point to the most energetic person, I want you to holler and shout. Good. We have a winner, right? So our first friend, whose name is Michael, and our second friend, whose name is Biwa. Sorry, did I butcher?
You say Biwa.
Biwa and our friend Michael are going to be photons. They are particles of light.
Yes.
You've always wanted this, right? They don't interact with the Higgs field at all. They can whiz around anywhere where they want to go. But there's one rule. Well, there's 2 rules. First of all, you have to wear a hat. Hat, please. And the second rule is you always have to be moving at the speed of light.
Oh.
Go! Good! Run! Good! Nice and careful on the stairs, but always move! Right. Our next friend, whose name is Evie, is a particle that has a little bit of mass. Put that down over your waist.
Okay.
Like an electron. So she interacts a little bit with the Higgs field. Run! That way! Run! As fast as you can, don't stop. Good. So she interacts a little bit with the Higgs field, but not too much. And our last friend, whose name is... Sorry? Eden. Eden is a heavier particle with a lot of mass. Come over here, please, Eden. Put that around your waist. So she interacts quite strongly with the Higgs field. Run, please. So she appears to have a lot of mass. So this is how different particles get their different amounts of mass, by interacting by different amounts with that invisible Higgs field. Are you running? Run! Good. Right. Stop. Well done. Give them a big round of applause. Woo! You okay? Well done. Good. Take that off. Well done, Michael. Thank you, Beaver. Thank you very much. That was awesome. That was good. Good workout, right? So, so that's my hypothesis, that different particles get their different amounts of mass by interacting by different amounts with the Higgs field. If you don't interact much, like a photon, or you don't interact at all, you have no mass. If you interact a little bit, you have a little bit of mass. And if you interact a lot, you're something heavier, like a W boson. Now, I can tell you, or I can suggest a hypothesis for how the particles get their masses. But I have to tell you that the Force from Star Wars exists. Are we all happy with this? As scientists, you're all happy with me telling you that the Force from Star Wars exists. Anyone want to say anything? Okay. There's a couple of you might be skeptical, and that's the correct way to be, right? But we can actually prove that this is the case, because if we smash particles together really quickly, like we do in the LHC, we can make that field ripple, right? And when it ripples, those ripples pop out as these little Higgs boson particles, right? So when you were clicking at the front, every time you got a big green tick, you were finding one of these little Higgs bosons. You were finding one of these ripples and proving that this field exists in the background. So there's an invisible treacle everywhere in the universe that you might not have even heard of before you came to this masterclass, right? Now, my favorite part of this presentation, the final part, it's called data analysis, yes? Now, why do we have to analyze data? Why do we have to analyze data? Question, yes. To make good conclusions. Another way of putting that is that human beings are stupid. Yes? Not just you guys, me as well, right? We fall into many ways of thinking that make us get the wrong answer. One thing we do is we make assumptions. Yes? Who thinks I wear glasses?
No, I don't think so. No, that's Charlie. Yeah. What?
So, I keep taking them on and off, right? Nerdy science guy has to wear glasses, yes? So, I've never worn glasses, right? Never worn glasses. So, we make assumptions, right? And assumptions are usually reasonable, right? There's no reason. It would be weird if you came up and asked if I'm wearing empty glasses, right? There's no reason for you to do that. So, we make assumptions. Another thing we do is we're hopelessly and incredibly biased, right? Here is a question. I'm going to demonstrate this to you, hopefully, right? How would you rate your physical fitness? 90. Very, very simple question. 90. Go to this website on your phone, right? If you go to that website, you will see a link which is called Just a Quick Question. Can you see that link? It's www.ministryofsense.com. Can you see that? Ministry of Sense. Ministry of Sense. Okay. Can we see the link? Just a quick question. Just a quick question. And you can put your answer to how would you rate your fitness. You can close it after you vote. You can do whatever you want. Now, I'm going to give you about 10 more seconds to get your answers in, and then we'll take a look. Right, yeah, you can play the other games. Please don't play the other games because they make noises, right? So, anyone want to shout out their answer? 5 stars, yeah. 5-star rated. I've seen some of you running around. I mean, the guys who came down at the front were pretty good, right? So, right. Let's take a look. So,
I'm super fit.
Good. I'm glad to hear, right? So, quiet please. So, when I ask, quiet please, because my throat's going a little bit as well, right? So, when I ask people a question like this with a range of answers, here's the honest answer that I would expect to see, right? It's called a normal distribution or a Gaussian distribution. Have you heard of that? Yeah? Normal, most people are normal, they're average, they're in the middle. Some people are Olympic athletes, and some people are not, yes? Now, I just asked you this question. There's about, what, 30, 40 of you? Do you think you gave me the honest answer that I would expect to see? Is it going to look like this distribution? Too much testosterone in the room. Yeah? Let's take a look. Right. Now, this isn't a perfect, I realize this isn't a perfect scientific test, right? Because there's a lot of testosterone in the room. There's a lot of people trying to play up a little bit, right? But, quiet please. This is the answer you usually get, right? Quiet please. This is the answer that you usually get. You get peaks at the edges, right? Peaks are awful, peaks are excellent, and very few people in the middle. When in real life, most people are in the middle, right? So why are we getting this? This is what we call a cognitive bias or a reasoning bias, right? This is the overconfidence cognitive bias. Makes sense why it would be called that. Because people judge their abilities as higher than they actually are, right? Your brain wants to be happy. It wants you to feel good, right? But that's not good in science, because sometimes the answer that makes us feel good is not actually the truth of nature, right? Now, if you go to the world's most important scientific research portal, which is
Wikipedia.
Yes, you're well on your way to being particle physicists. Well done, right? And you type in cognitive bias, we haven't even got past BI, and we've already got like 10 or 15, right? Ways of thinking that the human brain has to get answers quickly, but not necessarily correctly, right? 2, 4, 6, 8.
10.
Right, but what if the answer is not 10? Right? Your brain wants to follow patterns, but sometimes in science, the pattern doesn't give us the correct answer, and our brain falls in a trap. I'm going to show you a couple that are really important in particle physics, right? This is my favorite part. A nice graph. Number of deaths on US highways, and some lovely data. 1996, 97, 98, 99, 2000. The deaths go down as time goes by. What could be making this happen?
Safer cars.
Safer cars. So cars get safer as time goes by. Anyone else want to have a guess? Traffic lights. So we've got more control on the roads. Anyone else? Cats. All right, okay. More cats, so people have to slow down. Restrictions, right? So we have restrictions on the road, speed limits, things like this, right? Now, very, very sensible, good answers. But this is actually a graph of the number of US highway deaths against the number of fresh lemons imported to the USA from Mexico, right? Who thinks this is how we should make cars? That's the new Citroen, by the way. Yes, I know it's a bad joke, right? Now, why have I shown you? Yes, you liked it, did you? You like that joke? It's terrible. That's why it's good, right? It's so bad that it's good, right? Why have I shown you this image and this graph if they mean precisely nothing? Why do you think I've done that? Yes.
To show that people might think that two things correspond with each other, because over time they either decrease or increase together, so they're either directly or indirectly related to each other.
Well done, right? To show that just because two things look related, it doesn't mean that one causes the other to happen, right? We say that correlation is not causation. This is really important in particle physics, because if we're looking for something and we're expecting to see it, we always will. So we have to be careful that what we're seeing is actually caused by what we think it is, right? Here's another one. The number of people who drowned by falling in a pool each year, right? Because I love graphs about people dying, apparently, right? What's on the x-axis? What have you learned? Anything? Have we learned anything?
People who bought apples in shops.
People who bought apples in shops, right? The number of ghosts people say they saw, right? Yeah, number of kids going to whatever, right? It doesn't matter, right? In this case, it's the number of films that Nicolas Cage was in that year, right? And, oh, you know this one, right? Good. So, who thinks that this guy's films make people want to kill themselves? Okay. So in this case, right, there might be some causation with our correlation, right? But you can't just look at the graph. You'd actually have to like stand outside the cinema and ask people how bad the film was and whether they like want to kill themselves now, right? You can't just assume from the graph. The graph only gives the correlation, not the causation. Make sense?
Yeah.
Good. That's the first one. Now, this is the worst thing that humans do in their thinking. It is the worst crime that humans have in their brain, right? So there is a prize for this one. There is a prize for this one, right? A huge bar of chocolate at the end. But I need you to be as loud and as quick as possible. Do we understand? Spell ilk. Louder! Louder! Spell silk. Spell silk. One more time. What do cows drink? What? There was at least one milk over here, right? But most of you were good, right? Most of you have heard this before, right? And you did well with it, right? We've got to have someone say milk or this bit just doesn't work, right? So, somebody definitely said it because I heard it. It was me! Right? Well done. No chocolate for you, right? Good. The way to get out of this is to say baby cows drink milk.
Yeah, baby cows drink milk, sir.
Too late. Too late.
Honestly,
Too late.
I should go to the price.
Okay. All right. Well, I'll have a think about that.
Okay.
Right. So, why did our friend here say milk? Anyone want to tell me? Yes. Correct. Right. So this is what we call expectation bias or confirmation bias. Right. We build up an expectation, of what's coming. Ilk, silk. Our brain really, really wants to say milk. In fact, you can actually feel that it kind of hurts to say water, right? Does anyone notice that even though you know to say water, your brain is like, error, 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 yes? Because it's like me saying 2, 4, 6, 8 minus 57, right? My brain's like, what? It doesn't make any sense, right? So my brain wants to get me. It goes, yeah, I see the pattern. Yeah, we're all good, right? And then it falls in the trap, right? And this is really important because, again, if we're looking for a particle and expecting to find it, we're always going to find it because we fall in the trap. We guide our analyses towards it. We see it in our data because we want to see it. We have to be very, very careful not to fall into expectation bias. One more example in your everyday life of when you fall into expectation bias. Has anyone ever been singing their favorite pop song and they realize after several years that they never knew what the words were? Yeah. They've just been singing whatever the hell they wanted for ages. Yeah. And then somebody tells you what the words are, and how does your brain react? No, thank you. No, thank you. Right. So, this happens all the time. My mum does it all the time. Drives me nuts, right? You've seen these ones? Oh, wow. Once you see it, you can't unsee it, yes? Once you think he has a weird face, it's his hand on the gun, yes? But once I tell you he has a weird face and you look back, you can see it, right? This was my childhood, so you can start to work out how old I am, right? This was like, I was so good at this game, right? So once you see it, you can't unsee it. Another one, KFC, yes? Big head, tiny body, yes? Can we see that one? Yeah. Every time you get a KFC from now on, you will notice big head, tiny body, yes? Right? We do this all the time. Now, I was hoping to show you some music ones where we do this, but I don't know if these are going to play. They are going to play. Excellent. Right. The first one's been ruined, but never mind. Right. So, once you see it, you can't unsee it. I'm hopefully going to show you that once I tell you what to hear, you can't not hear it, right? And this is exactly how your brain decides in the first time you hear the song what the words are, yes? And it won't be told otherwise, yes? Because your brain is saying, oh, I know what that word is. It makes sense in context, and yes, it fits. And you fall into that trap. So What if I told you that Taylor Swift, any Taylor Swift fans? Good. Bit tay-tay, that's all right. Yeah, nothing wrong with that, right? What if I told you, you got to be quiet for these because you need to hear the story, right? What if I told you that Taylor Swift has psychic abilities? Because she knew it was Trevor before he even walked in. Yes? So, see if you can hear the word Trevor. Now I've made your brain hear it. Yes? This is how your brain gets stuck on a stupid word, right? What's the real word? Trouble, right? Trouble, right? Now, what if I told you that Rihanna...
Oh my God!
I'm going to ruin it for you. You called me sir as well. It's terrible, right? So, what if I told you that Rihanna likes to have personal relationships with the things that she puts on her chips? Yes? But that completely explains why she won't chew the steak. Too much mustard for Rihanna, obviously, right? So, they're really stupid, right? But once you hear the wrong thing, and I train your brain with some silly pictures, a few words, you can hear it, right? Here's my favorite one. I think I made this one up myself. Some of these are old, right? Whoa, hold up, Bruno. Right? Any Bruno Mars fans? Not for long. No, I'm joking, right? So, story on this one. Bruno Mars is absolutely in love with a local farmer's strange-sounding horse, right? His heart breaks every time he hears its neigh. The worst thing, though, is that it all just sounds like a cow's moo, right? Let's take a listen. Right, so they're really, really stupid. Say again? They're really, really stupid, right? But it makes an important... whoa, hold up. Right. This is where the point of the balls comes in, right? Right? Now, it sounds really stupid, right? But why have I shown you those? To show you that it's very, very easy, even in our daily life with simple things like song lyrics or looking at adverts, to fall into those biases, right? So when we're looking for a new particle, something that's fundamental to our universe, it's very, very easy to fall into those biases, and we have to stop ourselves. Now that we've done that, we can come to the end, and I can show you who did best on our little game. Let's take a look. So I can show you. Whoops, I think I need to come. Don't worry. So here is the data. Every time you clicked down at the front, a dot gets added onto this diagram, right? And the way that we find new particles is by looking for distortions, looking for bumps or peaks in these distributions. Now, does anyone think that they can see a peak in any of those distributions there? Yeah, maybe in the middle there. But remember, confirmation bias, right? If I tell you to see a peak, you always will. So we let the computer decide, right? We can see peaks all over this graph. There's little peaks here, right? We don't want those. We want the biggest one. So we let the computer go through and find the biggest peak in all of these data sets, right? So it looks like the computer finds a peak in both of your data sets, which means you did really, really well, right? And we can have a look at how significant those peaks are. So Team Atlas's score for today was 0.0002. Good. Good. Now, what does that mean? Maybe. Hold up. That means that there's only that probability that there isn't a peak, that this is just random noise, right? So if we flip it over, 99.9998 that you found something new. That's really good. So to win Team CMS, you need a score lower than that. Do you think you did it?
Yeah.
Let's take a look.
Oh, no, we did. Yeah.
So our winners today just are Team CMS. Give yourselves a big round of applause. Decimal places. Decimal places. Very close. People playing in the audience as well. Right, adds up all the data together, right? So the problem is there's 4 zeros, right, on one and 3 on another. You have to get the lowest value. So CMS is the lowest, yes? Yeah, so they win. Yeah. Okay, good. Now, the problem is when we want to find something new in particle physics, we actually need an incredibly high standard of evidence. We call it, yeah, that's very important, right? We call it the 5 sigma standard. Basically, a 1 in a million chance that this could just be a fluke. So we combine the data, and I'm going to combine the data from both of your clicking here at the front. And what you have to do to discover this Higgs boson in this room with us today is reach that red line. So this is all of you now, all of the data grouped together. Do you think you made it? The last school I went to, they didn't make it, unfortunately. You're going to make it? Okay. Let's take a look with appropriate music. Good. Just, right? So, individually, neither of you had enough data to discover this thing, right? You didn't reach the 5 sigma standard. I didn't give you enough time. Atlas and CMS, right? CMS did very slightly better, but you were very, very closely tied. Together, you didn't have enough data to discover this new thing. But pooling your play together and your data together, we can say today that you rediscovered the Nobel Prize winning Higgs boson for yourselves today. So give yourselves a big round of applause. Right. Given how well you have done, we are going to do the final demonstration. The final demonstration, as our friend already told us, is BIN. B-I-N, yes? Or what I like to call the baryon interaction nexus, yes? Now, what we are going to do, because you've listened to me for 45, well, more than that, an hour, you get to throw stuff at me, right? Yeah. You can throw that if you want. Good. I mean, you could throw all day because that's awful. Right. So, what we're going to do is we're going to make some particle collisions for real, yes? Hand these out as quickly as you can. This is our final demonstration. We can take photos and stuff at the end. Don't worry, that'll be that's fine. Hey now. Whoa.
The water in case it gets on the table.
This one?
Yeah, just in case it gets on the table. Because you don't need to be slipping.
That's all right. So,
Wait, you don't know what's happening. We turn them into stitch.
right. Here's what we're going to do, right? We're going to make some particle collisions for real, right? You've got your protons. Yeah! Oh, snap. I've got my high-tech particle detector. The BIN, yes? 3 rules. Here's what I want. As many collisions to study in the heart of my detector as possible. That's rule number 1, yes? Rule number 2. How many have you got? Rule number 2, right? You can keep throwing them, but please stay roughly in your seats. I'm going to go up one side, back down, up the other side, back down. So you get plenty of chance, yes? Right? So stay roughly in your seats. Rule number 2. Rule number 3 is the most important rule, right? As few in the middle of my face as possible, yes? Nobody listens to rule number 3, right? Count down from 5.
5, 4, 3, 2, 1.
Okay, ow! 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 Right, I'm coming across the front. Ow! 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 It's all right. Right, I think we're almost out of ammunition, so that's good. Right. Whew. Right. Here's the final thing that I need. Everyone on that front row, just grab as many balls as you can and put them in the bin here, please. Everyone on the front row, just nice and quick. Just come down to the front, nice and slowly, because there's a bit of water and stuff about, right? And just put any balls you can get hold of in the bin. And we're going to do the final demonstration. Right, be careful on the floor because it's a little bit slippy and there's bits of plastic about. Right, that's plenty. That's excellent. Right, that's good. Thank you very much. Spot on, spot on. That's enough. Not too much. That's enough. Thank you. Just chuck them on the floor. It's fine. Thank you. Good. Excellent. Right, go take your seats. Good. Right, take a seat now. Good. Right. So, here's what we're going to do. Have a sit down. Yeah, I want you to move back from your seats as far as you can onto the back row, just because we've got the space, right? So, nice and quiet, and I'll explain what we're going to do. This is the final thing, right? So, here's what we're doing. I've got some very simple objects, right? I've got your protons in the detector. They're going to collide, right? And we're going to have an explosion, essentially a particle collision, right? What I've got is a simple lemonade bottle, just from the shop, yeah? A little bit of lemonade still left in there, that's fine, right? A lemonade bottle. I've got some water, just out of the tap, and I've got a little bit of special stuff. Some dry ice, yes? Right, now, it's not as cold as nitrogen, right? I can't do it with nitrogen, but we do it with ice, right? Dry ice. Now, what I'm going to do is I'm going to take this bottle. I'm going to put 200 grams of dry ice into this bottle. Now, first question, and one of the teachers is going to pick who answers this so we don't just have a free-for-all. What is dry ice? Somebody want to pick someone to answer?
Easy.
Solid carbon dioxide is correct, right? So carbon dioxide is usually a gas in the air, right? People worry about it for global warming and climate change, but it's usually a gas in the air. Here, it's solid, right? And carbon dioxide is a little bit weird, like liquid helium. Carbon dioxide never actually becomes a liquid. It goes straight from being a solid to being a gas. Anyone know what we call that? Sublimation, that's right. So it goes straight from being a solid to being a gas. You can see the gas coming off the solid, right? Now, who knows the temperature at which carbon dioxide becomes a solid? Again, one of the teachers can...
Minus 80.
Good, yeah, about minus 80. Yeah, minus 70, minus 80, between those two values, right? So, what I'm going to do, like I said, put about 200 grams in here, and then I'm going to put in some water from the cold tap. What's the temperature of water from the cold tap?
20 degrees.
Yeah, probably 20 degrees today because it's boiling hot, right? 15, 20 degrees, something like that. What's going to happen to the carbon dioxide when I do that? Yeah.
It's going to bubble.
It's going to bubble, and it's going to turn into
Water.
gas.
Oh.
Going to turn into water.
Water vapor.
Alchemist, right? So, it's going to turn into a gas, right? What takes up more space? A gas or a solid? Gas, right? What's going to happen if I don't let it take up more space? By putting on the lid very, very tightly.
Explosion.
Yes? Explosion. So. About 200 grams in the bottom, yeah? We'll take the water from the cold tap, right? Right. This will be very, very, very loud, right? Even louder than you think it's going to be, right? If you don't like loud noises, you're free to leave, but do it now. It is extremely dangerous for me, right? Not for you. However, given that it's dangerous for me, I would appreciate if you were quiet while I did it, right? And then you can talk afterwards. Are we ready? So, nice and quiet, please. Run. If you're nice and quiet, you can probably hear what. Okay? Everyone happy? Good. Right, now the question, and this depends on the teachers as well, right, is, would you like me to do one more? Yeah! Teachers?
Are we up for one more?
Yeah! That's never the problem. It's just... Right, what I will need, and I want you to be careful because the floor is wet, is anyone who's close to the front, the first couple of rows, grab any balls you can see and put them back in the bin, right? Nice and slow on the floor because it's wet. Bottle is there.
We're in the splash zone.
What's me for?
Pretty much, I just want here.
That's lovely. That's lovely. Thank you very much. Right. Dry ice is available online if your parents are interested. Yes, only your parents. Right. Are we ready?
Yeah.
So it's going to be same deal, just 200 grams of dry ice. It'll take me a moment. All right, get my hands dry. So this is very, very cold, right? -80. You need to jig it around on your hands, otherwise it burns your hands if you try and grip it, right? So as long as I move it quickly in my hands, it's not too bad. But if I try and grab it, it will burn me. If you have on your phone, guys, if you have on your phone, most modern phones have like a slow-mo mode, yeah? If you record it in slow-mo, right, you can speed it up again afterwards, but it just takes more frames, right? So you can see the explosion nice and slowly. You can play it back in slow motion or fast afterwards, right? So I suggest that you record it in slow-mo. All it does is take a bigger video, right? More megabytes, right? But you can speed it up and slow it down afterwards, right? So if you want to get a nice video of it, slow-mo is really good, yeah?
Ready, sir?
I think so.
Ready?
I think so. Right, nice and quiet again, because, as I said, it's not dangerous for you, but it is for me, yes? So. Nice and quiet. Everyone okay? Everyone okay? They end up. Where? Where is it? Yeah, they end up all over the. Where? They end up all over the place. Right. Good. So that's the end of the presentation today, right? What I want you to take away from this presentation, more for you guys because you're learning particle physics, a little bit about that Higgs mechanism and that Higgs science. But most of all, what I want you to take away is the fact that anyone can do this, right? Anyone can do this high-level science. We did it in a bit of a weird way, but anyone can go through these steps of the scientific method. And they're so important in everyday life, even if we're looking at song lyrics or looking for a new particle or doing whatever it takes, right? Or in a court of law. It's very, very important to use these scientific methods and scientific ways of thinking to get around what our brain wants us to do. Most of all, I hope you just had fun. You did really, really well. So I hope you enjoyed it and have a lovely evening. Thank you very much.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.